What's up, guys? I'm happy to tell you that we are almost done with our mass balance course. We're going to enter this block, which is mass balance number 4. By the way, I'm your chemical engineering guy here, and we're going to continue with the transient state, which is a very interesting state. We've seen so far only steady state, which applies for continuous state, and this time we're going to see transient state, which is a very mathematical or analytically different approach from the algebraic equations seen before, but hopefully you understand and we can do some mass balances in transient state. So the content, before I start, I want to show you. Essentially, I just split the course or this block into two sections, which is number 1. Essentially, it's a little bit theory, review of transient state. Probably, if you remember, hopefully you remember, we've seen a little bit before in MP1 what kind of transient state problems we will be seeing, and we also saw that actually we're going to see 80% of steady state problems and about 20% of transient state. So this part here, 20%, is going to be covered in this block. So actually it's not that much. We've seen, so if you actually seen all my blocks videos, or MB0, MB1, MB2 and MB3, you probably just cover 80% of the course, and you understand essentially everything, what about the mass balance and etc. So we're going to review a little bit more in depth, so you understand what is transient state. Before, I just wanted to make you sure that when you cannot do continuous or steady state, that's probably a transient state. But now we're going to understand and study the transient state. So we're going to pay a lot of attention in this concept, which is the accumulation. Before, if you remember, it was inlet minus outlet plus production minus consumption equals the accumulation. Hopefully you remember that. We used the equation in every mass balance before, but accumulation was always 0. Magically it turned 0, so it was nice. Before watching chemical reactions, we just dropped the production and consumption, and our mass balances were essentially just inlet equals outlet. But we're going to see that that's not always the case. We have some times in which we actually are accumulating stuff or matter or mass. So we're going to follow a general methodology for transient state, which is not that different from the steady state. It's kind of similar to mass balance. We're going to add some section in which we try to use this accumulation concept, and we will apply some mathematical concepts, which hopefully you at least know or understand, which is the derivative, the integral, and you're not going to understand actually further on, because this introductory course you probably haven't seen differential equations, but don't worry, it's kind of easy. If you do understand them, you will have a easy time. If you don't know what that is, probably you shouldn't be worrying that much. Only understand the concept. If you can do the mass balance, the left, all the rest, other stuff, it's going to be only mathematical approach. So the important thing here, guys, is to do the mass balance equations, not that much to solve them. So we're going to see a lot of that. Probably we're going to finish into an equation or a set of equations, and I will tell you, okay, that's the set of equations, that's was the mass balance part. Now let's do the math, which is different. We can use analytical approaches or use computer approach or software for differential equation solving, etc. Now, once we understand the theory, we're going to follow the section 2, which is essentially some exercise in mass balance in transient state, of course. We're going to see the analytical approach, which I love saying, which is, or it is by hand. It means that we are going to use calculator and our pen and a paper, and we're going to follow those steps and do some equations. You have the equations, we do some math, and you got the values or answers. And we will see that normally the problems are kind of complex or long, or you need differential equations. So if you haven't seen differential equations, don't worry, because normally you just need to do the mass balance. Okay, we're going to do this. We're going to arrive to the mass balance equations, which you should do, or you should theoretically arrive to them. And then we're going to put these equations to a equation solver or a computer software that solves differential equations. So that's what we're going to see next. We're going to continue with section 1. As I said before, we're going to see a review, understand the accumulation concept, the general methodology, which is not that different from the steady state, and we're going to try to understand this guy, which is the differential approach. We've seen it before, and the integral approach, which is the one we're going to see here also. So, review, transient state. Hopefully you remember from MB1, we saw transient state, which is the value of any property in the system variable, or any system variable changes with time. The important thing here is time, because before we actually just saw like kilograms per hour, or pounds per second, or grams per minute, etc. And now we're going to actually change this stuff. We are not going to see rates, we're going to see intervals of time. So that's cool. Now, we talked about system variables. We're going to talk essentially about process variables, which are the pressure of a container, the temperature of a mixture, the volume of a tank or the level, the concentration of that tank or that flow, etc. The conversion of that reactor, it changes with time, of course. Maybe you are adding more flow, maybe the mole flow is increasing, decreasing, or the volumetric flow is changing because of these changes in pressure and temperature. And we're going to see this level stuff, which is essentially just you have a tank, or at least many people prefer to measure it as level. You see the level of the tank is 1 meter, or I don't know, 3 meters. And if you know the area or the diameter of that tank, you can actually calculate the volume. So when I speak about level, just try to assume it's kind of a volume related variable. I'm going to give you some examples so you understand what we are talking about. That process variables that change in time. So many times if you're starting with a reactor and all, I don't know, let's say A turns to B when you hit it, so you put here heat, maybe you're going to experience viscosity changes, not only because the reaction is changing a substance, but also because you're adding heat, which normally implies increasing temperature. So the viscosity may change. So we don't want that, or depends on the case. If you're operating in a, how to say this, in steady state, you're going to look for the viscosity to be the same. But essentially, if you're actually, for example, you have this mixture and you want to increase viscosity, you will probably heat it, evaporate water, and it will be kind of sticky like honey. So that's a transient state, because you do this and it takes a little bit of time and then you take it out, like in a batch. Also concentration, conversion of a product line, that's typically in a batch. As time passes, let's say the product concentration increases, which is what we want, because we want to produce our product. We don't want it to disappear, we want it to increase in concentration, which means it increases in mass. Mass flow also can be changed. For example, let's say we have this water and we're going like this, and you have different pressures. I don't know, this is like 10 meters and this is 1 meter. So essentially at first it's going to fall a lot or faster, and then as it goes down it's going to be a little bit slower. And what does that mean? Since the radius of the pipe is the same, it means that if we change the velocities, we are going to actually change the volumetric flow. We change the volumetric flow, of course, if we suppose same density, we're going to change the mass flow. So that's a kind of example. Now, of course, we can also speak about mole flow, the same case, but I like to, or I will prefer to use this as, for example, in combustion. If you're changing temperature, for example, combustion, you have one temperature, and you continue and you have another temperature, and you continue and you have another temperature. Temperature is increasing, and probably a lot of reactions or side reactions are happening there. So the final reaction or final components will be different as time passes by, because as time passes by, temperature will increase. Level of tank, of course, we're going to talk about. Okay, I have this pipe here and I'm going to fill it with water, and eventually it's going to get full. And if you continue, it's going to spill out. Total volume, same case here. We're increasing the volume of the system. Changing pressure, of course, temperature increase of a mixture. Typically, if you mix them, I don't know, maybe you mix A and B, and then you have different temperature and densities. Okay, that may happen also. Density of the feed changes. That might be because the weather outside is changing, and since the weather outside is changing, maybe you are, I don't know, because it's getting colder, you will get a density which is higher. And the type of reaction, as I told you before, in the example of combustion, as you change the temperature, other side reactions are going to react, or some that were inert, for example nitrogen, normally reacts with oxygen if the temperature is so high. So those kind of stuff is going to happen in the reactor. And finally, I told you before, in this example, I told you the velocity changes, and if the velocity changes, the volumetric flow changes. So those are some examples of application of the transient state when there is a change in time. Normally, when you produce, you want to achieve a continuous state, so everything can be understood in advance. You can calculate everything. You know how much kilos are passing per hour, etc. But in the transient state, you are more interested in the final destination, the final product. So what type of transient state problems are going to be in this course? We're going to see, for example, the typical one, which is batch. It's simply you fill a tank, you make it react, and then you discharge the tank, and you start all over. It may be a reactor, or also it may be, I don't know, mixing. You put A, you put B, and you have no reaction, you just want to mix them. You mix them and you got C, which is many common sense. For example, you have you want a 60% sugar and 40% water combination. You just add sugar and you just add water, mix them, and you get them. Maybe, I don't know, you need to heat it and stir it for 3 hours. That will be our final destination, will be at 3 hours. So you do it and you get your product. Semi-batch, for the other side, is for example, when you're starting continuous process, this part here, the starting part here, the startup, will be called as a semi-batch. Now, I don't mean that all transient states are batch or semi-batch. It's, for example, if I have this and this, and I have this huge square here. Transient state is all this square, and you may find either batch or semi-batch, or in this case, we're going to see that even continuous processes can be taken as transient state. When? Okay, let's see it. Continuous processes are always transient when we're going to start them, or start up. So let's say you want to achieve a temperature, you're going to heat until you achieve this temperature, and then you are going to call this your continuous process. For example, you know or probably have heard about iron or steel ovens. They need to achieve huge temperatures, and they probably take months, 1 month, to achieve this temperature in order to start producing. So in this month, we're going to see that every day we're going to increase or see an increase in temperature. So that is the typical transient state. We're going to achieve one temperature in order to produce in continuous process, but in the moment or meantime, we're going to have this transient state. Also, and I love this one here, is the modified in operation conditions, either increase or decrease. And I want to tell you guys that actually continuous processes are almost impossible. Eventually, if you make a very small interval of time, you're going to see that the density will change, I don't know, from maybe 999 and will vary to 1001, but in general the average will be 1000. So we can treat this as continuous and you will have no problems. But what happens, for example, if I tell you this oven operates at 1100 and you're using this amount of heat, I don't know, I'm going to use this probably, because we're producing, I don't know, 1 ton of steel. And imagine they tell you, okay guys, we just came from the operation unit area, and the manager or the operation director told us that we need to increase the production by 50%. So we're going to produce half more, not 1 ton, but 1.5, which that obviously means we're going to get or burn more combustibles or fuels. Then this implies that we're going to increase our heat requirement, and not only that, we're going to affect this, because if we just add some matter here, some steel, the temperature will drop. Why? Because you have the same heat here, you will need to increase a little bit the temperature, and the Q here of your system, let's say, forget about the temperature, let's see, the Q, it's going to increase. You're going to increase it because you just increased the mass flow. So in this moment, the time you start, of course there's going to be a plan. You're not just going to drop everything like, okay, just increase the flow and add Q. No, we're not going to do that. They probably are going to do it step by step. They're going to increase a little bit, maybe 100 kilos, and they're going to use Q. They're going to let it stabilize for some hours, and then they increase another 100 kilos, and then they start increasing fuel consumption, and then we wait for the stabilization, and so on until you get to this quantity, guys. So this state, it's going to be the transient state, because we are revamping, we're increasing our production, and therefore we need to increase this. You will see later in automation and control processes that you cannot just say, okay, just drop it and instantly will turn to the desired values. No, actually there's a huge problem here in the chemical industry. You need to wait for the variables to set. So if you just say, okay, increase it in 50%, you're probably going to have problems, guys. Now, let's see this final one, which is shutdown. Normally, if you want to shut down this oven here, or this furnace, you don't just simply turn off everything, because the temperature drop will be so extreme that probably you're going to have crackings everywhere. You're going to destroy your oven. The furnace is going to be cracked everywhere. You're going to have air inside, and you will make a chaos. So what you need here, guys, is to do the same thing we've done before, but for a shutdown. So probably you're going to decrease your fuel consumption. I don't know, maybe some kilograms per day. You're going probably to reduce temperature in a very slow way. Maybe, I don't know, 10 degrees per hour. It would take a lot of time, yes, of course, but you need to let the material or the oven walls to rest, because if not, they're going to contract and destroy and generate cracks everywhere. So hopefully you understand why do we have these in continuous processes. It's not that the actual continuous process has it, it's only that when we start it and when we shut it down, or when we changed normal operation conditions. This here is very common, guys, especially in today's world, when everything, they tell you, okay, we need to increase, and then 1 month later they say, okay, no, we have a stock, so you need to decrease, and the sell guys or all these guys aren't selling that much, so we gotta decrease, or we just find another client, we gotta increase, blah blah blah, increase, decrease. So it's a lot of action here, and we need to dominate this transient state. So if you dominate that, probably you're going to just say, okay, no worries, I have my plan, I will do it anyways. So it's easy. So here's an example, so just to let you know why the startup is kind of interesting part of the continuous processes. Imagine we have this medicine which actually has, I don't know, maybe 5% or 10% of the actual component that makes you feel healthier. So we have concentration X here, we have time here. And I don't know, in our viscosity we're talking about concentration, the concentration of the reactor. They tell you normally that here, when you add heat, you increase the temperature, of course. Hopefully you understand that. And if we increase the temperature, we're going to increase the reaction. And the products are more viscous, or let's say, ignore viscous, concentrated. So, what happens here? Just analyze this equation. No, not equation. This graph here goes up, down, up, down, up, down, until it gets to a value which is the desired value. We want X here. So, now, you have X here, and as you can see, guys, maybe you add some heat, and the reaction goes itself and generates a lot of temperature, and because it has a lot of temperature, it will increase in concentration of X. Now, this here, let's say it has 50% here, this is 10%, and this is 5%, and actually you want, I don't know, 4%. And this will be 3, and this will be, actually, this will be 0. Anyways, let's say you can only deviate, let's say we have 4 grams here, or 4 grams per liter. You have this line here, that's our goal, our set point. And they tell you that you can only deviate 1 gram per liter, so you can go either here or here. So, the first, I'm not going to talk about seconds nor days, I'm going to speak it later, tell you later. But imagine this first section here, it's 1 time. This section 2 is second time, 2 times 2, and then 3 times time, and this is 4 times. So before we can use our product, let's see, this is out of a specification, out of a specification. You cannot use this, it's so variable. Probably you will not like to send this to the client because he's going to have a very variable product and he will not like it. But eventually, probably here, you start having control. It's inside parameters, so you have it, perfect. So this is the breakpoint, which is about 3.5, let's say 3.5 times. So now let's use this. If it were seconds, probably you don't care. 3.5 seconds, it's nothing, you can wait all. Probably you will say, ah, okay, 3 seconds, I can actually wait until, I don't know, 10 seconds. But imagine it's days, guys, and you're producing tons of product. You have this reactor, huge reactor, and you cannot stabilize the product. Imagine you need 3.5 days to stabilize that product, which is probably, I don't know, you think it's a little bit, I think it's a lot. Imagine 3 days going to the work or to the plant and see the reactor not producing what you want. You're just dropping all these materials. Probably if you're, I don't know, let's say you're producing 48 tons per day. And I don't know, it costs $10 the ton. You are throwing away $400 per day, which will be eventually like 1,000 something dollars. So that's why we need to understand the mass balances in transient state in order, of course, we're talking about here reactor engineering and kinetics and momentum transport, mass transport. But if you do not understand the mass balance here, you will not be able to do the other stuff I told you before, engineering, reactor engineering, all engineering stuff related. So once you understand the importance of transient state, you will see why is it important, especially when starting up and shutting down processes. So that was a little bit introduction of what was the review of the transient state. Now we're going to see what's the concept of accumulation here. So in this case, I just want to tell you that unfortunately accumulation is not zero. So from our last equation, inlet minus outlet plus production minus consumption, you will get this value here, accumulation. And the thing here is we will not be able to take it out. We cannot do it. Why? Because we are actually accumulating matter or mass in our system. And the bad thing, I don't think it's bad, it's only mathematics, is that we are going to turn that value probably into derivatives, which is derivative of mass with respect of time. Why time? Well, the first time we actually used time in this equation, because before we didn't use time, but right now we're going to use it because time implies, well, if you have seen integrals before, you see initial time and final time when you integrate. So that means we are going to have a delta of time, which means we're going to start from a, I don't know, probably time 0, and you say what happens in 10 seconds and what happens in, I don't know, 1 minute. You're going to be asking that yourself, because probably if you have this system and it's increasing in pressure because it's producing, I don't know, you're producing CO2, you want to know how much CO2 you're going to produce in order to relate it with pressure, in order to know if you're going to blow this thing off or not. So it makes sense to study this. Now, as you know, or hopefully know, anything that relates a derivative, for example, any function of y and t that relates this derivative, it's called a differential equation. And normally, if you want to solve it, you need to add an initial state, or any state actually. But what we're going to see, it's the initial state, probably because that's the state you have. You see right now in time 0, which is time equals 0, I have a volume of, initial volume of, I don't know, 10 liters. That's the typical, because it's the one you're measuring right now. So yeah, just know that, guys. If you don't know it, please make a little bit reading in differential equations, maybe just the intro. But if not, anyways, we're going to continue. So before we got these algebraic equations, which are very, very nice, only x and y and equals numbers and plus and the division, etc. And the thing here, we're going to turn to differential equations because we're adding this derivative concept, which turns into differential equation. The good thing here, guys, probably you've seen first order differential equations. We can do them technically easy. It's not that hard, and I call this doing it by hand. So you can use a paper, a calculator, and your pen, and eventually you can solve it. You're doing some methods, etc. You get to the answer. The bad thing here, guys, because I'm pretty sure you're in the introductory level and you haven't seen differential equations that much, it's that when you got second order differential equations or third order or even multiple second order or multiple first order, you're going to do this by computer, guys. And especially in mass balance, because we are engineers, we're not interested in how fancy do we do our math problems. We're interested in getting the result. We're not going to get with the clients and tell them, oh, look, all this. I do this pretty math, look, this method, so nice. And the answer is, I don't know, this number. They will prefer a guy that say, okay, I got this value. And of course, the first guy took, I don't know, 1 day. Let's say he took 1 day. And this guy, in the other hand, he just made the mass balance, put the equations in the software, and in some minutes, he got the same number. Of course, they are going to prefer this guy. They don't care who is mathematically nicer, who had the best assumptions, blah, blah, blah. No. The guy that is going to win is the one who goes faster. So that's why if you're like more mathematical oriented, probably you're not going to like this that much, because we're going just to put all the equations and click solve. And we will get, of course, our answer. One important thing here, and I'm also pretty sure you haven't seen that much numerical methods, it's that we're going to use this stuff for both types of differential equation, first order and second order, or even more higher orders. And yeah, guys, just make sure don't get lost. I'm going to add some additional info. You have no idea what I'm talking, which I will be at the same, if I were you, I will be the same, like what the hell is this numerical method? I'm going to add some links so you can understand, but don't worry. If you do know what I'm talking about, you probably are fearing these guys here, differential equations, and especially these ones here, because you know that doing them in software it's easy, but by hand it's almost a headache. So let's continue. We were talking about the accumulation, about how they produce differential equations and so. Now, let me give you an example. We have a tank, and they tell you that water flows into this tank. As you can see, there's no outlet, so water doesn't flow out. It's going to accumulate, going up, up, up. And the next process variable are going to be affected. Probably you know the logical one, which is volume. And since the volume is increasing, the level of the tank is going to increase as well. And you know that volume is related to mass with density, so also mass is going to increase. And since moles and mass are related by molecular weight, we're going to increase also mole content. And the problem here, guys, is when you're starting to make your problem a little bit more complex. You have one inlet and you have one outlet. So they tell you water flows in and flows out. We're going to see these three cases. When the water goes in equals water that's going out, the thing here is we're going to have a steady state, which is nice because we're not going to accumulate. Probably you know the level will stay the same because I'm adding 5 liters, but at the same time I'm taking 5 liters out. So it stays perfectly fine. We can do our mass balances as before, no transient state needed, and we will not have increasing level, nor mass, nor volume. As time passes by, you're not going to change the conditions or variables in the system. But what happens, guys, when our water flowing in, it's a little bit lower than our water going out. In this case, guys, we're going to have transient state. Why? Because we are actually emptying the tank. So you have this level, and let's say you have 2 liters going in and you're taking 5 liters. You know that eventually it's going to drop, the level is going to drop, level is going to decrease, the volume of course is going to decrease, and since volume is almost related to mass because of density, and we're going to suppose density is constant, the mass also decreases. In time, or as time passes by, the tank will get empty. That's why we need an accumulation and a derivative of mass with respect to time, or derivative of volume with respect of time, or even derivative of level with respect of time. But what happens when we have 10 liters and we're still taking only 5 liters out? Well, you will know we're going to increase the level. We're folding it. We have a delta of 5 liters. So we still have a transient state. We're filling the tank and we're going to increase the level, the volume, and the mass. What will happen with the tank as time passes by? It will get full, and after getting full, it will spill out because you're still having water. If you close the inlet, probably you're going to avoid that spilling, but if you're doing this process and you do nothing, you're going to eventually spill the tank. What I want to do here, guys, it's this, we've seen this before, a subset of units. We have, as you see, tank 1, tank 2, and global system here. Let's call this tank 1. Let's call this tank 2, and this square global system. Let's analyze the global system. As you can see, no change in mass. We're just changing here water here to this here, but actually the liters here and the liters here are the same as the liters in total. So you have 5 liters here and you have 2 liters here. The total will be 7. Even though you may, I don't know, change this, for example, 5 liters in the tank 2 and in tank 1 only 2 liters. The mass has not changed. We haven't added, or we did not add water. So we're also going to ignore the level, which is doesn't make that much sense here. So we have a steady state. But what happens when you analyze tank 1? You will have a transient state here, which is because the outlet is actually inlet is 0. Because the inlet is 0, we have outlet, and we're going to empty the tank. If you wanted to do a mass balance in this system, you will have a transient state equation. And yeah, tank number 2, transient state. We're going to speak, there's no outlet, there's only inlet. We're going to fill the tank eventually. And yes, guys, here we have also a transient state equation. This is derivative of mass with respect to time. You have this derivative of mass with respect to time. And all these will be accumulation equals 0 because you are not having in the system inlets or outlets. Now, as we said before, we got various systems, tank 1, tank 2, and this here. Some may be modeled as transient state, for the case of this guy, and others may be modeled as steady state. The thing here, guys, is that you need to know what they are asking you for. If they tell you something about the system, you probably can ignore this and this. But if they tell you how much time does it take the tank to full, of course you will need to use a transient state. But if they tell you how much mass is being transferred to the overall system, you don't need to do an accumulation analysis. You have your equation and you just do it. Now, before we've seen only one component, but we're going to see what happens when we have two components. We're going to do the same. We're going to fill and we're going to empty a tank with salt and water. So we put water and we put salt. We are going to have an initial level of volume of the solution. So we have already water inside and salt inside. Therefore, we have a concentration of salt here. Now, we take out the solution because we're going to mix them. We mix them and then it goes a solution out. What I wanted to tell you is that depending on the levels and volumes and all that, water is going to accumulate, salt is probably going to accumulate, and yeah, I wanted to show you these here. Water and salt flows. When these two guys are larger than this guy, when these two guys are equal to this guy, and when these two guys are lower than these guys, or are a little bit less than these guys. And we have, as I told you, a salt concentration. Now, I bring you this table, guys, because I wanted to show you all the possible cases and to show you the complexity of this problem. In this axis, you have the, let's say, overall mass balance. In this axis, you have the salt or A mass balance, which is also interesting. What happens, for example, let me take out this. I want to analyze first when the feed, let's say feed, it's bigger than the solution or larger. What happens that, of course, eventually it's going to spill. Even though you don't care if the concentration or the feed concentration, the initial concentration, you don't care because you're talking about mass here, which turn into volume. It's going to spill. Eventually, if you add a lot of water and salt and you wait in time and you're not taking out in the solution, the tank is going to spill. Now, what happens when the feed equals the solution? So you're putting something in and you're putting something out. The level will stay the same, of course. In every case, you don't care about concentrations. The level will stay the same. Now, what happens when the solution is going faster, or it's going out faster than the water here? It will, of course, get empty. Now, guys, that was the overall mass balance. But I want you to put here a little bit of attention, pay attention here, and analyze it. When the initial concentration in the tank is bigger or larger than the feed in the concentration. It will actually dilute because you're increasing the amount of feed, and the feed is not that concentrated, so it will get diluted. Now, what happens when the initial concentration of the tank equals the feed concentration? The concentration will stay the same. Concentration is equal to the initial. And finally, guys, what will happen if you have a larger concentration in the feed than the initial concentration? It will concentrate, of course. You're adding a concentrated variable, so with time you're going to concentrate it. So I have just another one thing to tell you. Maybe you haven't noticed before, but we have a continuous process here. And remember that continuous process means as time passes by, there's no change. So here this will spill, so we ignore this. And what else? Level stays the same. This makes sense. Level stays the same. Okay, all these guys are useful. And empties. Empties means that we're not having that we are having a change. Now, when the system dilutes means that we are changing the concentration in time, so we don't need this column, and here also not. So we just dropped everything that changes, and the only value or the only process in which the process is continuous is when the level stays the same. That means water and salt equals solution, and the concentration equals the initial one with the feed one, which is also this case. So from 9 cases possible, we just arrived to one continuous process, which is very interesting. This one here. So anyways, let's continue the concept of accumulation. We have our equation here. We're going to analyze now differential balances. As before, it's about rates and velocities, and integral balances, which is the change of finite substances in time. And as I told you also, we're going to see this methodology for transient state. So let's speak a little bit more about the differential mass balance. We will need time intervals because we are speaking about rates. And that means we need to apply some boundary conditions. The typical boundary conditions are initial time and, of course, I don't know, volume of time 0 or pressure of time 0 or mass flow of time 0, etc. Compared to the final time. So we are going to have a change in time or a time interval. So if we're talking about rates, mass per time, we're going to multiply by time, so we get mass. So we do it, input, output, production, consumption, accumulation, and we get this equation here. The change in mass of the whole system is going to be the mass in the inlet, the mass being generated or the production, the mass going out, of course negative, minus the consumption of here. We get this and we multiply by time because we know these are rates, so we know this is mass divided by time. So if we multiply by time, we will get mass, which is actually what we want, the change in mass. So continuing, we divide this equation by delta t, and we use delta t, we try to approximate it to 0, which is the definition of derivative, and you get this. Derivative of mass with respect of time is equal to these rates. But not only that, guys, we need the boundary condition. So we're going to apply the boundary conditions later. Now that we know how to do the balance, I'm going to present you the methodology, which is number 1, write an expression for the amount of the balance quantity in the system, which is, of course, inlet minus outlet plus production minus consumption equals this term here, which is the interesting one, accumulation. Set the accumulation term in the balance to the derivative of the mass and time, of course. So essentially we do dm equals dt. Substitute in all values of inlet, outlet, production, consumption. This could be numbers, this could be equations, whatever. Just solve them and put them in this equation. Now, I told you before we need to transform this into a differential equation. So this will be the accumulation. These functions here will be inlet, outlet, production, and consumption. And this here, guys, I told you typically as time equals 0, you will need to know a value, a starting value. If you don't know it, then it's kind of difficult or impossible to solve it. So please try to find it. And if you have many equations, please do as many as you need. Now, this is a recommendation. You don't need to do it, but it helps a lot, especially because it's something graphic. You will remember everything if you need to increase or decrease the quantity. You gotta sketch a plot of y versus t. In this case, y will be mass and t will be time. If it increases, decreases, stays the same, etc. Now, as I told you before, you probably have this equation. If you can solve it by analytical approaches, go ahead and solve it by hand. And you will get the value. Probably this is the typical problems in exams, because you get to, as a teacher, you get to know if the student has the knowledge of mass balance and the ability or mathematical abilities to solve it. Now for the other side, guys, if you are not able to solve this, or it's kind of difficult, or I don't know, there's many reasons why you cannot solve a differential equations. Maybe you haven't seen the course of differential equations, so you are going to probably use a computer software. You put all the equations and click in the magic button solve or go. So yeah, it's very simple, guys. I have an example so you can practice the methodology. Click pause so you can read, and then I will read it for you. So we're going to talk about the differential balance on a chemical reactor here. We're going to speak about a continuous stirred tank reactor. Well, it's a tank or a reactor. We're going to produce R, liquid phase. Here's the reaction. You have this volumetric flow entering. You have the concentration entering. Yeah. Actually, CA initial. The volume is B, and of course it will stay the same. You can suppose it's perfectly mixed, so you have no problems with density and concentrations. Actually, they remark it here. They tell you that the rate of consumption of A, they are so generous, they give it to you. It's equal kCa times liter of reaction volume. Okay. They tell you, please write the differential balances on the mass and A. So in total mass, overall, and moles of A. And they tell you you cannot solve it. Of course, you have no data, not numbers, but you can get the equations. So you have this system, the tank. Let me actually go to my drawing, which will be, you have this volume flow, you have initial concentration, you have concentration going out, you have density going out, which is the same. These guys are the same. You have total volume and the volumetric flow out. The first thing I told you before in the methodology is do an overall mass balance. Include the inlet, outlet, and accumulation in this case. Why only that? Because we're doing an overall mass balance. There's no production nor consumption of mass, so you can take out this. You get this equation here. Good. Now, since we know that the mass is related by the density, or volume is related to the density and mass, we use this equation, and okay, we just wait for it. Number 2 says set the accumulation term in a derivative form. So the accumulation here, you know, it's always the change of mass divided by the change of time, which is the derivative of this here. I'm going to substitute mass. It's volume times density divided by time. And since density is constant, I can take it out. And I got this derivative of volume respect of time. The inlet is simply density times volume in, and out is this here, volume here and here. So number 3, let's say substitute data and equations into inlet, outlet, and accumulations, which we already got, so that's good. We only substitute here, here, and here. Since density is constant, we take it out. That's only math. And we get this equation. And of course, we need this equation to be a differential equation in order to solve it. What does that mean? You have the derivative here, you have this here, but you need to add the boundary limits. So don't forget the boundaries, which are here. At time 0, you have a volumetric flow of 0, of initial. I didn't include this the plot. I don't think it's necessary. So I just jumped to number 6, which says simply solve. But remember, guys, that they ask us mass balance general and overall mass balance and balance over A. So we're going to repeat in, out, production minus consumption. I like it this because we are actually including these guys here. Now, we want to find the moles of A. We're going to speak about moles, and eventually you can change, you can change this to mass, so don't worry. Moles of A are given by this and this. And since the accumulation in this case is moles of A, the derivative of moles of A with respect of time, you get this. Because this is this, you substitute here. Inlet is just this, outlet is just this, and you're done. You could also, if you're speaking about mass, just be sure that the concentration is given in mass per volume. And if not, normally they tell you concentration moles per volume. So take care. So once we got everything, we just substitute. And we here, this consumption here is very important. This is from the kinetic. Actually, let me go here. They tell you here this times volume. The consumption of A, normally they will not tell you this. You will need to know about reaction kinetics, but because you're in mass balance, they will tell you, so don't worry. They told you that you can get the consumption only with this. So you need the K, which will be a number, a constant. You need the concentration, which probably you have it, and you will, actually concentration will be the variable. This will be our variable. And the volume, which probably you either know it or you're going to calculate it. So we got our equation here. We substitute all the data as before. Accumulation, inlet, consumption equals accumulation. Inlet, outlet, consumption equals accumulation. And of course, don't forget to add the initial state, which is at time 0 you got concentration in 0, which means initial concentration. And that's everything, guys. You will have 2 equations. Actually, you only need 1, so you can choose. I don't know. You have concentration and volume are your unknowns, and you have 2 differential equations. So that's very cool. We have 2 equations and 2 variables. The only thing here, guys, that you are probably worrying about is that we have not a normal equation, but a differential equations. So if you don't know how to treat them, but you can achieve this. If I were your teacher, I will be okay, you know everything about mass balance. The only thing is that you haven't been in the course of differential equations, so I think it's cool and I take it as correct. Or if your teacher is such a mother son, I don't want to tell that, but he will tell you no, you still need to solve it. This means nothing, which is true. If you get with these equations to a client and they tell you what the hell is this, you need to solve and get numbers so people understand. So that's, I think, the scope of the course is understanding mass balance, not being an engineer with clients and showing results. So I think with the equations by themselves are okay. So next topic, and I think it's the last topic in this section, is about integral mass balances. Now we've seen how to do differential mass balances. Are going to see how to proceed with the integral mass balance. The thing here is that we use finite amount of time, which is delta t. So we use what happens in 5 minutes, what happens in 10 minutes, etc. And because of that, we get finite amount of mass. We're going to use an approach with integrals, of course. Don't use that much imagination. You need integrals to do this, guys. Now from this same equation, you probably remembered, it's in, production, out, consumption, you get this. And the thing here, guys, is that we are going to actually change this here to here. So you have all these terms as derivatives. So you integrate this with time, of course, you will get this change of mass and this differential equation and this differential equation and integral. You have four integrals, which is the integral of inlet, integral of production, integral of outlet, integral of consumption. All these will give you a delta M. And before doing the exercise, I just want you to tell you that it probably seems so difficult to solve, but many are going to be constants. And what does that mean? For example, you have one constant, you have the integral of T0 and Tf. You solve this as T0, it's only at T, which is Tf minus T0. And normally T0 is 0, so you're going to actually just do this. So this thing that looks so fancy turns only to be C times Tf. So don't worry, it seems like very complicated. You can do it as complicated as you want, of course. As you want to be precise, you're going to increase the difficult and expressions of math. But don't worry, guys, it's only math. Let's do it. Please click pause and read the video. I'm going to wait for you. So let's continue. The water level in a municipal reservoir has been decreasing. So you have this decrease. Okay, water is decreasing, probably because of consumption and evaporation. Blah, blah, blah. Okay, it's going to continue 60 days. So they are telling you already how much time. So T0 will be obviously 0 and T final will be 60. Hopefully you know that, guys. They estimate, I don't know, they are so cool. Water companies know about math. They tell you they have this consumption. Probably they mix it, they measure it, or I don't know. Okay, and this State Conservation Service, probably full of engineers because they give you this expression, which is kind of interesting. They tell you 10 to the 6th times the exponent of minus time divided by 100. So this is what the input is, what water is going to fall from the skies, also called rain. So we have an inlet, we have this consumption. We're going to see later that this is not actually a consumption, but an outlet. But okay, let's take it. Now, they are asking you how much time do we need to get to this number if the rain is like this and your consumption is here. So one thing here, guys, we don't actually know if we are going to increase or decrease because you need to use this equation. But probably, let's be optimistic, and we're going to suppose that this equation is going up faster than the consumption here. So, write a differential balance on the water in the reservoir. We're going to do that. And they tell you integrate the balance to calculate the 60 days. So, let's do it. We follow our approach, or our mass balance methodology for transient states. Get the mass balance equation. So it's here. There's not production of water, there's not consumption of water. There's only inlet, which is the rain, and outlet, which is the how much they drink, the guys drink, or everything, evaporates, whatever. Equals the accumulation of the system. And I don't like to use these, so I use these letters. They look cool. Now, number 2, set the accumulation term into a derivative. So actually it's here. This is my derivative of accumulation. Substitute data and equations. I have this here. This is inlet, this is outlet. We take out densities and we get to this final equation. We are going to talk about volumes, which is cool because density is constant. Now, substitute 1 and 2, which is this, number 3. So we have 1 here, which is C, and 2 here, which is inlet. So I substitute this here, this is one term, minus the consumption equals the accumulation. So this is accumulation, this is consumption, which is actually not consumption, is outlet, and this is the inlet. And we transform these to differential equations. So only we have our derivative here, we have our function here. We only need to add the initial state. And they tell you the initial state is 10 to the 9. So we are ready to solve it. They tell you to sketch a plot, but it's recommended. I didn't include it, so I continue to solve it. I can solve it, yes. Now solve for t equals 60 days. So how much volume am I going to have then? We have these equations. I tried to solve for t. Okay, I change the differential to the right. We continue. Now I integrate from initial volume to final volume and initial time to final time. So this is time dependent and this is volume dependent. So because it's a constant, I just multiply by v and I need to substitute this data. I used differential. I split this in two, which is easier. I told you before this is going to be a constant. So I've substituted some data. I substitute here and then 60 and 0, 60 and 0. And then I know that the initial value is 10 to the 9, so I substitute it here. I know that if I solve this, I get this equation. Hopefully, this is math, guys, don't worry. We do some math and I just look for final volume, which is, I change this to here, positive. I do this right here and this here. At the end, this is whole math. I'm not going to stop on that. So the only thing I wanted to show you is the final volume here. I got the final volume and yeah, guys, that's what I'm being asked for. First thing they tell you, write the differential equation. We wrote it and the final volume, we find it. So the differential equation will be this here. This will be your first, let's say A here, and the B or final volume will be this here. So cool. We are finally ending our section number 1. Hopefully you understood what we've seen before. We saw a review of transient state. What's the difference between unsteady state and steady state? When can we have transient state in continuous processes, etc. Most importantly, we saw and analyzed the accumulation concept, how to use it. Normally, or in general, it's a derivative of mass with respect of time. And we saw how to treat integral versus differential values. So you can do a mass balance either by integral method or by the differential mass balance. I do like a little bit more this one here, but you should know both, because sometimes this is so easy. You just have the integrals, and you are just adding. Differential sometimes take a little bit more. And what we are going to see in section number 2, it's some exercises, which is mass balance in transient state. I call it by hand. Probably we use some numerical method or so. And we're going to see computer solved mass balances in transient state. So this is kind of interesting. So see you in the next video, guys, if you're still interested in solving mass balances in transient state. What's up, guys? It's me, chemical engineering guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. So thank you guys for the support and the love.